Hello friends, my name is Chinmay Deshpande. In this video lecture, we are going to discuss about a topic from unit commitment. The name of a topic is constraints in the unit commitment. Now, what is a spinning reserve? The spinning reserve is the term which is used to describe the total amount of a generation which is available from all the synchronized units on the system minus the present load and losses being supplied. Now we know that from economic load dispatch, I write it the equation equality constraint, whatever will be the demand, that much amount of generation should be. Now when we talked about the losses, then we should write it here PL, that is PG will be equal to PD plus PL. So if I write it like this, PG minus PD plus PL, I will get this equation which is equal to 0. So this term is nothing but what? Spinning reserve. So here I have written total amount of generation available from all synchronized units. So that's why this is PG minus present load, that is what is the demand, PD, and whatever will be the power losses associated with it. Now the synchronized units on the system may be named units which are spinning on the system. The spinning reserve must be carried so that the loss of one or more units does not cause too far a drop in the system frequency. Quite simply, we can say if one unit is lost, there must be an ample reserve for the other units to make up for the loss in a simplified time period. I'll give you a simple example. Suppose if I have money of rupees 1000, my daily expenses are 800 rupees. Now, if I minus this, how much money will be? 200 rupees with me. Now suppose there is a one person who asks me, I want 100 rupees. Can you give it to me? I'll give it to back once once I have that money. It's okay. I don't have any issue. So what I did, as it is required to have 100 rupees to that person, I have given whatever excess amount of money that I have to him. So this is what is the case of a spinning reserve. But the important condition is that whatever will be my daily expenses, let's say it is 800 rupees. Apart from that, is there any 100 rupees, 200 rupees with me? Yes, I have. That's why I have given it to the other person. The spinning reserve must be allotted to obey the certain rules which is usually set by a regional reliability councils that specify how the reserve is to be allotted to a various units. The typical rule specifies that reserve must be capable of making up for the loss of the most heavily loaded unit in a given period of a time. The spinning reserve must be allotted among fast responding and slow responding units. This helps in automatic frequency control in the event of generation outage. So this is what is the formula. Whatever I have written here, the same formula is there. Total generation output of all synchronized units at a particular time minus load at that time, which is nothing but PD, plus losses at that time, which is equal to PL. So this is a spinning reserve. Now let's say PGSP is the spinning reserve. So it is denoted as this is your spinning reserve. PGI is nothing but it is the power which is generated by I number of units which are synchronized with each other. PD is nothing but a total demand on the system and PL is the total loss in the system. So this is the formula for the spinning reserve. Now, what are the thermal units associated with unit commitment, thermal unit constraints? A thermal unit can undergo only a gradual temperature changes, and this translates into a time period of some hours which is required to bring the unit online. Due to this, a gradual change in the temperature, various constraints will be arised in the thermal unit operation. First one is a minimum uptime. Now what is the meaning of a minimum uptime? If the unit is running, it should not be turned off immediately. I'll give you a very simple example. We know that water boils at 100 degrees Celsius. Let's say if the temperature reaches up to 95 degrees Celsius and the water is about to boil and it will be converted into, let's say, steam. Now suppose if I remove the burner on which the utensil is there and in which the water is kept. If I remove that burner, what will happen? Now, no more heat will be given to the water and it will not boil up to 100 degrees Celsius. But after some time, now suppose if I want the water temperature up to 100 degrees Celsius, then what we have to do? Again we have to connect the burner. Again we have to put a burner on which the utensil should be kept. Now, as we have removed this burner, if the temperature reaches up to 95 degrees Celsius, then it will be reduced, let's say up to 90, 80, like that. Now I want the water up to, I want temperature of the water up to 99 degrees Celsius. So again I have to heat that water, I have to provide heat to that water. So in that case, the time which is required to reach from that 80 degrees Celsius to 95 or 99 degrees Celsius, it is more. So once it is running, it should not be turned off. So this is the meaning of minimum uptime. If we have a generator, if we have a unit, we are using it, if it is running, it should not be turned off immediately. Similarly, the minimum downtime is nothing but once the unit is decommitted. Decommitted is nothing but what? The meaning is if the unit is turned off, there is a minimum time before it can be recommitted. There has to be certain time so that it will be turned on again. And third one is nothing but a crew constraints. Now, if the plant consists of 2 or more units, now we cannot start it immediately or we cannot start both at a time. They cannot both the turn on at the same time since enough crew staff members are not available to attend both the units while starting up. If the number of staff members are less, then how it is possible to taken care of both the units? It is not possible. So this is the one constraint which comes under a thermal unit constraint. Now the next one is nothing but a startup cost. The temperature and the pressure of the thermal unit must be moved slowly and a certain amount of energy must be expended to bring the unit online. This energy does not result in any megawatt generation from the unit and it is brought into the unit commitment problem as a startup cost. I'll give you a very simple example for this. Suppose if I have a two-wheeler and there are two persons who are sitting on the two-wheeler. The total weight is, let's say, 100 kilogram. Now I have started my two-wheeler and if I raise the accelerator at let's say when the speedometer shows 10 or when the speedometer shows 5 like that, it will not move from one point to another point. Why? Because the total load on the system is more and some kind of energy will be utilized to counterbalance that total load. So take this analogy in the same way. When the temperature and the pressure of the thermal unit, if it is increased and the certain amount of the energy is expended to bring that unit online, the energy which is expended, that doesn't mean it will immediately produce some amount of a power in a megawatt. No, it will brought into the unit commitment problem as a startup cost. The startup cost can vary from a maximum cold start value to much smaller value if the unit was only turned off recently and is still relatively close to the operating temperature. Now there are two approaches to treating the thermal unit during its down period. So what are that two approaches? Let's see. First one is a cooling, second one is the banking. Now here the cooling is nothing but allow the unit's boiler to cool down and then heat back up to some operating temperature in a time for the schedule to turn on. So this is the definition of a cooling. Now what is the formula of startup cost when cooling is to be done? It will be what? It will be Cc into bracket 1 minus e raised to minus t upon alpha into F plus Cf, where this Cc will be equal to what? It is cold start cost, which is in MBTU. It is what? The British thermal unit. It is a traditional major unit of energy which is approximately equal to 1055 joules. Now the British thermal unit is almost replaced by SI unit in the energy, which is nothing but a joule. So F will be equal to what? This F will be equal to fuel cost. Then C, if you see CF, it is nothing but a fixed cost. This will be a fixed cost, last term which is present, which includes the cost of a crew members or crew constraint. then maintenance and the expenses, which is in rupees. Whatever here alpha that we have written, this alpha is a thermal time constant of the unit, and T is a time in R the unit was cooled. The next one is nothing but a banking. Sufficient energy is inputted to the boiler to just maintain the operating temperature is nothing but a banking. So how we can write a formula for this? Startup cost when banking is there. So here instead of cooling, here we have to write startup cost whenever there will be a banking. So please make a change here, which is equal to what? Ct into T into F plus Cf. Where this Ct again, it is the cost of maintaining unit at an operating temperature. F is the fuel cost. Cf is the fixed cost that we have seen earlier. T is the time in R the unit was cooled. So the cost for the two can be compared so that if possible the best approach can be chosen up to a certain hours. The cost of the banking may be less than that of the cost of a cooling. It is but obvious. So this is the graphical representation. Here on a x-axis we have taken time in the R. On the other hand, on the y-axis we have startup cost. So the graph whatever we will get, this curve whatever we will get, this is the curve of a cooling and this will be the curve of a banking, which is almost a straight line, but it will not pass through a origin. Some amount of distance will be there from the origin. So this is the graphical representation of cooling and the banking. Now there are few other constraints also in a unit commitment. Third one is the hydro constraint. Now unit commitment cannot be completely separated from scheduling of hydro units. But the startup cost and the time of these units are generally low in case of hydro units. It can be assumed that the hydrothermal scheduling can be separated from the unit commitment problem. Now neglecting the hydro constraints may not give an accurate result of the optimal solution. So what is the first hydro constraint is the must run. What is the meaning of this must run? Some units are given a must run status during a certain time of the year for the reason of voltage support on the transmission network or for such purposes as the supply of the steam for uses outside the steam plant itself. And next is nothing but a fuel constraints. A system in which some units have a limited fuel or no fuel or else have constraints that require them to burn a specified amount of the fuel only in a particular period of a time, it will present a most challenging unit commitment problem. So these are the constraints in the unit commitment. So what are the constraints? Already we have discussed. First one is nothing but spinning reserve. Second one is the thermal unit constraint. In that we discussed about minimum uptime, minimum downtime and crew constraints. Then next is the startup cost. And the third constraint is the hydro constraint, wherein we discussed about a must run and the fuel constraints. Thank you for watching this video. If you have any doubt, please feel free to ask the questions. Thank you once again.